Over the past few videos, we've been talking about these properties of limits, and as you can see, I've got the first two up here, and the first two are pretty obvious. And also, I'm going to say right now that the first two really always hold, and you can kind of think about them always holding because they really are pretty special cases, right? We've just got a constant there, so we say the limit as x goes to a if some constant is just equal to that constant, and also if we had the function just f of x is equal to x, and we were to take the limit as x approaches a, that would just be equal to that value a. And so hopefully those are more or less somewhat obvious, and I hope that now especially you have an intuitive feel for what these first two rules mean. And what we're going to talk about in this video is really all of the other rules. And if you remember, I don't know if I did a great job of explaining it, but I said that after we cover these two rules, that all of the other rules in our list sort of have this precondition, this one guideline that they have to fit in order for them to apply. And that was that, let's say we have, and we're going to be dealing with two different functions, the limit, let's say the limit as x approaches a of some function f of x, and the limit as x approaches a of some function g of x. And what we said was that in order for every other rule that we had, and you remember, maybe I should have written them down, but those rules were that that we could sort of distribute this limit operator over a product or over a sum or into a ratio. Or into a power, so long as it was a positive power, or so long as what we were distributing into the power was non-zero. And hopefully you remember those rules. But the precondition for all of those rules, was that both of these limits, the limit as x goes to a of f of x and the limit as x approaches a of g of x, both of these had to exist and be finite. They had to exist and they had to be finite numbers like 2 or 7 or pi or whatever constant. We couldn't have one of these limits be equal to infinity. So anyway, one of the questions that you might be asking yourself is, what can we say about limit problems when we don't have this condition met? Say we had some function, and let me actually go ahead and I'll do an example. Let's take a look at, and this will be sort of our example function, the limit as x approaches 0 of 1 over x squared. So now let's just go over here and let's graph that function really quick. Let's graph the point at 1. So when x is 1, 1 over 1 squared is just going to be equal to 1. And when x is negative 1, 1 over negative 1 squared is just 1 over 1, which is 1. So we have that. And as we choose numbers that are really, really close to 0 from either the positive side or the negative side, we're going to be squaring those numbers, so even if those numbers are negative, we're going to be always dividing by a positive number. So you can think that our values for this function, we've got a positive 1 on top, and we're always going to have something positive on the bottom. So our function is never going to dip below the x-axis, right? We're never going to be able to, let me just define this. F of x is equal to 1 over x squared. Because whatever value we put in for x, we're always going to be squaring it, so we're always going to have a positive number divided by a positive number. So therefore, we're never going to have anything down here where y is negative, right? And as we choose numbers that are really, really close to 0, we're going to be dividing 1, and let me say this, that we're going to be dividing 1 by really small numbers, and that's going to yield a really big number, right? It would be like multiplying, if we divide 1 by 1/100th, it would be like multiplying 1 by 100, right? If we divide 1 by 1/1,000,000th, it would be like multiplying 1 by 1,000,000. So as we get really close to 0, the function is actually going to grow to infinity. So this is what our function is going to look like. And the same thing is going to happen from the positive side. And those two graphs should have looked a bit more equal. Maybe I should try to actually I'll just redraw this side. So it comes down and it asymptotes along the x-axis in either direction, and it asymptotes along the y-axis over there. So this is the graph of our function. So now we're asking, well, what is the limit as x approaches 0 of this function 1 over x squared? And hopefully you can see by the graph, and hopefully you can sort of tell intuitively, that we couldn't just plug 0 into this function, right? And it's not going to, we're not going to, and sort of there are a number of different rules a number of different preconditions that this function is going to break, right? I'm going to erase this stuff. If you remember, so maybe this particular function is going to answer a lot of different problems. Like if you remember, we said that the limit as x approaches a of some function f of x, all of that raised to the k. Remember that we could say that we could move that limit inside. This is going to be equal to limit x approaches a, f of x, and all of that raised to the k, provided that k was positive or that this function was not equal to 0. And we haven't met either of those conditions, right? Because you can imagine our function f of x is just equal to x, and our k is equal to -2, right? So this is like saying, you know, the limit x approaches 0 of x raised to the -2. So now we're sort of seeing what happens when we've broken this rule, and we obviously have a discontinuity at that point. We have our function that's growing towards infinity. It's not going to approach any particular value, right? Because if we divide 1 by 0, that's going to be undefined, so we're not going to approach any particular value there. And as we get really, really close to 0, the closer we get to 0, the more this function is just going to grow. It's just going to keep growing and growing and keep growing exponentially the closer we get to 0. So therefore, what this function is going to be equal to, let me just erase some of this stuff so I can write this down. What this function is going to be equal to, it's going to equal infinity. Because as we choose numbers that are really, really close to 0, we're just going to get numbers that are bigger and bigger and bigger. If you say that, okay, we're looking at, you know, x is 1/1,000,000th, then 1 over 1/1,000,000th is a million. We looked at x as being 1/1,000,000,000th, or I guess it's a million squared. So 1 over is actually or x is 1/1,000,000th. So therefore, I guess the value of the function at that point is a million squared. So you can see that the closer we get to 0, the more this function is just going to grow. It's never going to approach any definite value. So therefore, this function is going to be equal to infinity. So now, the question I want to ask, and I've still got a few minutes left in this video, is what happens if we plug this into, let's say, our first sort of, the next sort of limit property that we defined after the first two that kind of said we needed these two conditions in order to evaluate it. So let's say we had, and if you remember what that was, we said that the limit as x approached some value of f of x plus some other function g of x, that we could distribute this limit inside this operation, right? Limit f of x approaches a, plus limit x approaches a of g of x. So now let's see what happens when one of our functions, let's say that this 1 over x squared function, that's going to be our f of x. And let's just define some other function. Like let's say to demonstrate this rule, say this is an example. Let's say that we're going to take this first function, limit as x approaches 0 of 1 over x squared. And we're going to add to, or we're going to say that's our f of x. And we're going to add to that plus, I don't know, plus x, let's say. So we're going 1 over x squared, or else actually no, let's actually do two functions. Let's say plus x plus 2. So now we should be able to, by this rule, break this function up into 3 different limit problems, right? We can distribute this limit operator, you can sort of view it as, amongst these 3 different functions that we have. So let's go ahead and do that. We've got the limit x goes to 0 of 1 over x squared plus the limit as x goes to 0 of x plus the limit as x goes to 0 of 2. So now you might be wondering, well, these 2 over here, these are pretty simple. This is just going to be 0. This is just going to be 2. And those follow very closely from those first 2 limit properties that we set up. But now we've got this term over here. We've got this term that doesn't fit our rule. And we already know what this limit is equal to. So we know that this is going to be equal to infinity. So if you were faced with, let's say, this problem, and we've broken it up and we've solved all of our separate limits, we have the limit as x goes to 0 of 1 over x squared plus x plus 2. What would you write down for your answer? Would you write down, we figured out all of these different things. We've got infinity plus 0 plus 2, and let's just even get rid of that 0 and just say infinity plus 2. Hopefully you can see that this 2 doesn't matter. Infinity is infinity. Infinity plus 2 is still infinity. Infinity plus, a billion is still infinity. Or infinity minus a billion is still going to be infinity. So you can't treat infinity as sort of a regular number. You can't say, infinity minus anything finite is still going to be infinity. Infinity plus anything finite is still going to be infinity. Infinity times anything finite is still going to be infinity. So therefore, what we would write down if we were faced with this particular problem, it would just be equal to infinity. So anyway, there is an example of a limit problem which wouldn't really fit the rules that we had set up for our limit properties. In the next video, maybe I'll do this for the other properties of limits that we had set up, and you can see that we're probably going to expect similar answers out of those problems. So anyway, I'm going to end here, and I'll see you in a future video.